Thank you very much, Valerie. In this talk, I would like to discuss the possibility of intelligent life elsewhere, assuming that we have one here. Some of us are still in doubt, reading the newspapers every day. The question, are we alone, is, at least in my book, the most fundamental question in science. Because one way or another, it will change our perspective about our place in the universe and about our future as a civilization. We would feel much more responsible to take good care of our planet and everything around it if we were alone. And in fact, just a few days ago, the Nobel Prize was awarded to two people that discovered the first planet around a star like the sun. It was also given to the person that helped develop our model of the Big Bang, the universe, how it started. And these are interrelated questions, because we would like to know not only whether we are alone, but when did life start in the universe, how long it has been going, well beyond the few million years that we heard about just before. Now, we thought that we are at the center of the physical universe. We had a picture where the Earth was at the center and everything else was moving around it. And then Copernicus helped us understand that we are not that central. In fact, the Earth moves around the sun, and there are many other planets doing the same. There are many stars out there, like the sun, and presumably they have planets as well. But many of my colleagues still believe that we might be at the center of the living universe, the biological universe, that we might be unique or special. And you might wonder, how come they dare to think that, given the history of science? And the answer is that it's a very natural human tendency, and I learned about it from my two young daughters. That's a picture from when they were very young, and they tended to think in their youth that the world centers on them. And we as a civilization follow the same path. It's quite natural to believe that you are at the center of the scene because you see everything around you. But then, as my daughters matured, they realized that they are not at the center, that in fact there are other kids on the street, some with qualities that are better than they have. And so the interesting question in our context is, are we the smartest kid on the block? Not only whether we are alone, but if we are not alone, what else is out there? And we will mature in that sense only once we find evidence for others on the cosmic street. Now, looking at the sky, I often tell my students, looking at the sky makes you modest, because you realize that you are just a small piece in the big scheme of things. In fact, when I read history books and I see emperors or kings that were boasting about conquering a small piece of land here on Earth, it looks ridiculous, because, in fact, there are more grains, there are more planets like the Earth in the observable volume of the universe than there are grains of sand on all beaches on Earth. So an emperor or a king that was boasting about conquering a piece of land here on Earth resembles an ant hugging a single grain of sand on the landscape of a huge beach. It's not very impressive. The sky teaches us modesty, and we better listen to that and be humble and not believe that we are special or unique and that things are centered on us. And one way to figure it out is by collecting data on what we see on the sky or traveling there. So another way to put it is, as I mentioned before, are we the smartest kid on the block? And if you look on Earth, conditions allowed biology to develop the way we see it. But if you look at cookbooks, you find that you can start from the same ingredients, mix them together in different ways, and end up with different cakes. And some cakes taste better than others, depending on how you put the ingredients together. So it's quite conceivable that the same ingredients that we find here on Earth were mixed in other ways on other planets, and perhaps those cakes taste better. In other words, these beings are more intelligent than we are, much more technologically mature by now, and we can learn from them. And so, without having a prejudice, we should simply search. And what I'm really struck by is why this question and this motivation is not in the mainstream of astronomy. Because I can tell you from the experience I had over the past year at least, the public is extremely interested. This is the most interesting question that the public cares about. Yet, it's outside the mainstream of science, even though we have the technology to address this question. And that's something I don't fully understand, because if the public is interested and the public is funding science, then scientists should address this question. Why aren't they? And of course, the explanation is psychological. There is the literature of science fiction. There are reports that on unidentified flying objects that are not substantiated to the level of scrutiny of science. And so scientists close themselves in ivory towers and say, this subject is not something I would like to be engaged in, because we better be careful about making statements when there is so much public interest and much of the discussions that people have are not at the scientific level. Well, my approach is quite different. I say, if the public cares about it, and since it's such a fundamental question, let's use the best tools we have, the best ideas we have, to make progress and address it. And in fact, science is not an occupation of the elite. It's basically an activity that is driven by curiosity. It's basically what all of us did as kids. We were trying to figure out what the world is like without having a prejudice, without being attached too much to our egos. It's not about impressing other people. It's not about getting more likes on Twitter. Science is about figuring out what reality is. And you do that by having a dialogue with nature. Not a monologue in which you say what you think nature is. You say it's very unlikely to have life out there. Instead, you go and explore. It's a dialogue with nature. You let nature educate you. And that's what we should do in this context as well. And I don't see any difference between the pursuit of this question and the pursuit of a question like, what is the nature of the dark matter? How did the universe start? What are black holes? These are all scientific questions, and we should apply the scientific methodology to address them, especially questions that are of interest to the public. So that's my take on it, and it takes me a while to try and convince my colleagues to bring it into the mainstream. I haven't succeeded yet, but I'm doing my best. And so, in exploring the answer to this question, we should look up. We tend to look down, we tend to focus on what's going on here on Earth, but there is another dimension. We live on a two-dimensional surface here on Earth. There is the third dimension, and we better look into space and do something like archaeology, by digging into space, excavating space, and looking for signatures of other civilizations that may have existed a long time ago and may not be around anymore. I call it space archaeology, but we can find evidence for them, just as we do when we excavate the ground and find evidence for ancient cultures that are not around anymore. And the first place to start is in our backyard, right? Because that's most accessible to us. So what is our backyard? Our backyard is the solar system. And the First, the object that is closest to us in the solar system is the Earth. And in fact, we can discover objects that arrive to us from outside the solar system. How will we do that? Well, these are called meteors. Meteors are objects that burn up in the atmosphere as they enter, as they are on a collision course with the Earth. And almost all of them originate in the solar system. So they're not interesting. They're rocks that were left behind from the formation of the solar system. But every now and then, there may be an object that is not bound to the sun, that came into the solar system from outside, that we could explore. So in fact, earlier this year, I found this archive online of all the meteors that were discovered over the past 30 years, and I suggested to an undergraduate student at Harvard that works with me to try and extrapolate the orbits of all these meteors that were reported and figure out if there is any one of them that may not be bound to the sun. If you go back in time, you would figure out that it actually came from outside the solar system if it moves too fast. And indeed, we uncovered one that may be interstellar in origin. It was discovered back in 2014, and it had a speed of about 40 kilometers per second relative to the solar system when it entered. The data comes from a system of sensors that belongs to the US government. So the US government released the data on the speed of this object, but without error bars. The error bars were classified for obvious reasons. And so currently we have the editor of the Astrophysical Journal letter identified a referee that has security clearance to look into the data and see whether indeed this particular object is interstellar in origin. So that's a very unusual situation. We're waiting the results of that. But in principle, interstellar meteors that are big enough could leave a meteorite behind that would land on Earth, and that's our best bet for putting our hands on a piece of technology from outer space. We just don't know of any such an example, but it's a possible way of making progress. The next place to look is on the moon. So the moon is different from Earth in the sense that it doesn't have an atmosphere. So nothing burns up in the atmosphere. In that sense, it preserves everything that falls on its surface. That's a good thing. Even small objects make a small crater, and we see all these scars on the surface of the moon. And so you can think of the moon as a fishing net for everything, collecting everything that is on a collision course with it. Moreover, the moon doesn't have any geological activity, so it doesn't mix up things that end up on its surface with the inside. And so, in principle, by looking at the surface of the moon and examining the surface very carefully, we could potentially find interstellar debris, material that came on a journey from outside the solar system that landed on the moon. And we could potentially search for signs of life in that material. So if there was a piece of rock that came from the habitable zone around another star that ended up colliding with the moon over the past few billion years, we might find the traces of that on the surface and potentially learn about those distant locations without the need to visit them. We can just search on the surface of the moon, and indeed NASA announced its goal to go back to the moon by 2024. So this would be an interesting science project to excavate the surface of the moon and search for interstellar material. And one can identify that material by finding isotopes that do not have the same ratio as they do for the solar system. So you can tell whether some material did not belong to the solar system to start with. Of course, there are many objects that passed through the solar system and didn't collide with any planet like the Earth or any moon. And that material can be viewed in real time. So the first report on an interstellar object, an interstellar visitor, was on October 19th, 2017. About a couple of years ago. And what was strange about it is it's just like having a guest for dinner. You open the door, and the guests come in, and you notice that this guest is very strange, nothing like any other guest you had before. And you wonder what this guest might be, but by the time you realize that it's so strange, the guest left out into the dark street and you cannot watch it anymore. So that was the experience with this one. It was discovered by a telescope in Hawaii, pan-stars, and is called Oumuamua, which implies in Hawaiian a scout, a visitor from far away. And it was very peculiar, this one. First, as it tumbled, the amount of light that was reflected, the amount of sunlight that was reflected from it, varied by a factor of 10 or so. And that's unusual. We've never seen an object within the solar system with such an extreme geometry. And that means that it's either cigar-shaped with a length 10 times longer than its width, or pancake-shaped. And in fact, a pancake shape is preferred by the most detailed analysis of the tumbling of this object. And so it looks strange in that regard. It was not expected. The abundance of objects of this size was expected to be far smaller. I wrote a paper a decade earlier saying that we would not see anything with pan-stars. It also was at rest relative to the local population of stars in the vicinity of the sun. So if you take the average of all the random motions of stars in the vicinity of the sun, there is the so-called local standard of rest. And this object was at rest in that frame, sort of like a buoy sitting on the surface of the ocean, and then a ship runs into it, the ship being the solar system. It's, aside from its shape being unusual, it also appeared to emit very little heat, and so its reflectivity was quite high relative to objects from the solar system. And most importantly, it deviated from an orbit that one expects just based on the sun's gravity. So its orbit exhibited an extra push. And usually, such a push is provided by cometary outgassing, when an icy object evaporates due to heating by sunlight. But there was no cometary tail to this object. There was no dust, no gas detected in its vicinity, no water or carbon-based molecules. And so a puzzle arose as to what gives it the extra propulsion. And the only possibility that we thought about with a postdoc of mine, Shmuel Bialy, was perhaps the push comes from sunlight that is reflected off it. And if that's the case, and if it's pancake-shaped, then maybe it's a solar sail. Maybe it's a sail that is being propelled by light reflecting off it. We mentioned that in a paragraph in a scientific paper that was accepted for publication within a few days. And I didn't regard this statement as unusual compared to other statements in papers that I've written years before, for example, about the nature of the dark matter. Very often you put out a hypothesis with the hope that more evidence will be able to test it, rule it out or rule it in. In this case, the reactions were much more extreme, and I still don't fully understand why. The second interstellar object that was reported just about a month and a half ago is 2I Borisov. It was discovered by Gennady Borisov, a Russian engineer, amateur astronomer. And this one looks just like a typical comet in the solar system. So I was asked, doesn't that convince you that Oumuamua must have been natural in origin as well? And my response is that if you walk down the street and you see a weird person, and following that you see a lot of normal people, that doesn't make the weird person normal. In fact, it's exactly the opposite way around, because you realize how unusual the first object was. But in principle, one can estimate the abundance of objects like Oumuamua that was estimated to be about 100 meters in size, an object like 2I Borisov that is estimated to be about 1 kilometer in size. This object, Borisov, shows a cometary tail at a distance that is 10 times farther away from the sun. And, you know, the story of this one being natural and typical and Oumuamua being special resembles my first date with my wife. You know, I felt that she's special on that date, and I have never met anyone like her since. And so the fact that I met many other people later didn't change my opinion. And the same applies to the first two interstellar objects that were reported. Now, one can imagine interstellar objects of this type that are trapped in the solar system. If they pass close enough to Jupiter, Jupiter gives them a gravitational kick that could bring them into a bound orbit around the sun. And one can calculate how many such objects should be trapped in the solar system. So in principle, the sun and Jupiter trap objects in this way. And after a while, these objects are lost from the solar system because their orbit is unstable with some characteristic time. So we estimated that about 6,000 such objects are expected to be in the solar system that have roughly the size of Oumuamua. And identifying them would allow us to study those objects in much more detail than we were able to with Oumuamua. So that's something to look for in the future. And of course, one can, in principle, study their composition by doing spectroscopy of any gases that come off them. The easy way to identify them is by the highly inclined orbit that they have relative to the orbital plane of all the planets in the solar system. Most of the debris from the formation of the solar system is still orbiting in the same plane. But these interstellar objects arrive to the solar system at some random angle. And so you can easily pick them up by the inclination of their orbit. And there are some highly inclined objects that were already identified that one can study more in the future. And one can also estimate how frequently will such trapped objects collide with the Earth, for example. And there should be quite a large number of them that collided with the Earth. And that is potentially interesting because it's possible that life was brought to Earth from outside the solar system. It doesn't solve the question of the origin of life because you still have to produce it elsewhere. But if life can be transferred between planetary systems, potentially you don't need many sites in which life forms. that will seed the rest of the galaxy. Now, if we move farther out, we could search for signatures of artificial light, for example. So you can ask the question, how can you tell the difference between an object that produces its own light and an object that simply reflects sunlight? Well, a simple way to do that is by seeing how the object dims as it goes away from us. If it reflects sunlight, the amount of light that is impinging on its surface goes down as 1 over the distance squared. And then there is another factor of 1 over distance squared as to the brightness of the object seen by us. So altogether, it dims like 1 over the distance to the 4th power. Whereas if it produces its own light, the dimming will reflect just 1 over distance squared. So by seeing how objects dim as they move away from us, you can potentially tell whether they are producing their own light or reflecting sunlight. So an interesting calculation that we have done is how far can you see, for example, a city like Tokyo? And the reason we chose Tokyo is because the numbers were out online about how much light it produces. And it turns out that you can see a city like Tokyo all the way to the edge of the solar system, to the Kuiper belt. So potentially, with existing telescopes, we can see an amount of light produced by an artificial source of light, be it a spacecraft or something else, all the way out to the edge of the solar system, with the Hubble Space Telescope, for example. As we move out of the solar system, and here you can see a diagram of all the planets on the way out, beyond Neptune, which is still relatively close to us, there is the heliopause. That's where the solar wind, the material that comes off the sun, that's where it meets the interstellar medium. And that's roughly at 100 times the Earth-Sun separation. So once you go to 100 times farther than the Earth is from the sun, you get to the point where the solar wind is stopped by the interstellar gas. But that's not the end of the solar system. That's roughly where the Kuiper belt is. The solar system continues to the so-called Oort cloud that is much farther out. It's 100,000 times the Earth-Sun separation. Another factor of 100. And at that point, you are roughly halfway to the nearest star. So the nearest star is about 4 light years away. It's Proxima Centauri. And you can ask the question, is there life around that star? It turns out that this is a dwarf star, about 12% of the mass of the sun. Most of the stars in the Milky Way galaxy are much smaller than the sun. They would live much longer. All the stars are nuclear reactors. But these dwarf stars burn their nuclear fuel. Even though they have less fuel, they burn it much more slowly than stars like the sun. And most of the stars are much smaller than the sun, like Proxima Centauri. And they would live for up to 1,000 times the lifetime of the sun. They would live for up to 10 trillion years. There will be still nuclear reactors in the sky that we can look at, that we often call stars, when the universe will age by another factor of 1,000. And the sun by then will die. We will have to go somewhere else because it will be very cold here on Earth if Earth itself will exist. And then we will need to move. And the nearest star, Proxima Centauri, is a good place to think about. Now, it turns out a couple of years ago, there was a planet discovered around this star that is in the habitable zone of that star. Even though the star is fainter, if you get close enough to the furnace, you can keep yourself warm enough to have liquid water on the surface of the planet and potentially the chemistry of life as we know it. So this planet is called Proxima B. And it's so close to the star, it's about 20 times closer than the Earth is from the sun. It's so close to the star that it faces the star with the same side at all times, just like the moon faces us with the same side, simply because the gravitational tide managed to keep the planet in that orientation at all times. And so it has a permanent day side and a permanent night side, this planet. And my daughter, when I told her about this planet, when it was discovered, my 14-year-old daughter said that if we ever go there, she would like to have 2 houses. One in the permanent night side, when she can sleep, and the other one in the permanent sunset strip that separates the day side from the night side, where she would like to have her vacations. And she came across this idea when we visited Hawaii. You can see a picture there. So if you imagine yourself sitting on the beach of Proxima B, there is a place where the real estate value will be the highest, where you can look at the sunset all day long, throughout your life. Now, of course, life is what we define to be life as we know it. There could be other forms of life, and one of the fundamental questions is how to identify it and whether indeed there are many different possible cakes that were baked on other planets compared to the one we find here on Earth. There is a warning sign from Mars. That's a planet that had conditions that were suitable for life early on, but then it lost its atmosphere. Because life as we know it requires liquid water, and liquid water can exist only if there is external pressure. Otherwise, solid ice goes straight into gas if there is no external pressure. So in order to have liquid water and the chemistry of life as we know it, you need an atmosphere. And Mars lost its atmosphere because it's a smaller planet than the Earth, about 1/10 of the mass. So it lost its atmosphere, and then there was no more liquid water possible on its surface, and no life after that. But there could have been life before that. And potentially, life was brought to Earth by Martian rocks. We don't know. Perhaps we are all Martians. So the fundamental question is, does Proxima B have an atmosphere, as to whether we would like to go there or whether there is life there? And it's possible to figure it out without making the trip. You can just look at the light curve, the amount of light that you get from Proxima B as it moves around the star. And the permanent day side is constantly illuminated, it's hot, whereas the permanent night side is cold. But if there is an atmosphere, the temperature contrast between the hot side and the cold side will change because of winds, because of heat redistribution. And so just from the amount of light that you detect coming off the planet as it moves around, you can tell the temperature contrast between the permanent day side and the permanent night side. From the colors of the day side versus the night side, you can tell how different are the temperatures. And so that's one way to tell if it has an atmosphere compared to a situation of bare rock, because we know what the temperature contrast should be for bare rock. And in a couple of years, the James Webb Space Telescope will be launched into space, and it has the potential to tell us whether Proxima B has an atmosphere or not. So that would be interesting in addressing the question of whether travel agencies should advertise Proxima B as a good place to go to. And there are, of course, other stars not far away where we see multiple planets, some of which that are habitable. For example, the TRAPPIST-1 system that, as you can see, has 7 detected planets, and 3 of them are in the habitable zone. This one, again, is a dwarf star, about 8% of the mass of the sun. And there are 3 planets, potentially, that could host life there. and it's about 10 times farther than Proxima Centauri. So the journey will take 10 times longer. By the way, if you want to make the journey with existing rockets, it would take 100,000 years. So if you wanted to get there now, you should have boarded a spacecraft that left when the first humans left Africa 100,000 years ago. But that's with existing technology. The hope is that we can develop, as I will discuss in a few minutes, better technologies that can propel us, or pieces of equipment, to much higher speeds. We know that we would like to move into space because even though Earth is our home and we can do the best we can to preserve it, eventually there are all kinds of threats. Obviously in the short term, climate change, nuclear wars, biological wars, chemical wars. But aside from self-inflicted wounds of the type that we are creating due to our advanced technologies, there are external threats. Asteroid impacts, the type of impact that killed the dinosaurs. Solar flares. About 160 years ago, there was an event called the Carrington event that impacted the Earth and changed the temperature of the atmosphere by a few degrees. And if such a solar flare would have taken place today, it would have cost the world economy trillions of dollars, simply because we have all this technological infrastructure that was not there 160 years ago. We should worry about these external threats. They will not necessarily eliminate life, but they are obviously a threat to our technologies. And eventually, of course, the sun will die. So at that point, we will have to move out in about 1 billion years from now. Nothing to lose sleep about immediately, but eventually it's clear that we will need to venture into space. And the most comfortable way to venture into space is by boarding a spacecraft that would feel just like sitting in this auditorium. Now, what do we feel when we sit in this auditorium? We feel that we are pulled towards the center of the Earth with a gravitational acceleration of 1g. That's the force of gravity that keeps us bound to the Earth. If you shut it off, we would all fly into space. Okay? So we have this force of gravity, and Einstein, in his theory of gravity, educated us that if you board a spacecraft that accelerates at 1g, it would feel just like being on the surface of the Earth. There is no difference between gravity and acceleration that is artificially produced by an engine, a rocket engine. So imagine boarding a spacecraft that accelerates at 1g. If you were to do that, after 1 year, you will reach the speed of light. So it would feel very comfortable. It would feel just like sitting in this room. If you sit in the room for a year, you could, in principle, reach the speed of light. The problem is, you need an engine that will bring you to that speed, and it's a huge amount of energy. It's more fuel than we can imagine. So it's not practical, but it's possible. And the interesting point is that if you continue to accelerate at 1g, during your lifetime, you can actually traverse the entire universe. And that's because of time dilation. Time is ticking more slowly in your frame relative to the rest of the universe. So even though the rest of the universe ages by billions of years during that time, since you are accelerating very close to the speed of light, you can live through that journey. That's an interesting possibility. Now, how can we reach, let's not be so ambitious, but let's ask the question, how can we reach the nearest star within our lifetime? Well, one way to do that is to build a spacecraft that travels at a fraction of the speed of light. Let's say 1/5 of the speed of light, then it will take it 2 decades to reach the nearest star. How do you get to 1/5 of the speed of light? Well, conventional rockets are limited by the exhaust speed. They basically throw out material from their back end at some speed, and they get boosted in the process. But the problem with rockets is they carry their own fuel, so they can't really reach a speed that far exceeds, by more than one order of magnitude or so, the exhaust speed. And that's why all the rockets since Sputnik until now reach roughly the same speed of 30 kilometers per second. We haven't made much progress in that regard. So the way to circumvent this limitation is not to carry the fuel with the spacecraft. And one way to do that is by imagining a light sail. A sail that is being pushed by an external energy source that produces light that bounces off it and moves it forward. This is not a new concept. Shortly after lasers were invented, Robert Forward, back in the early 60s, imagined such a propulsion scheme. But what can be done nowadays that was not possible in the early 60s is that one can imagine very powerful lasers that are pushing on a very lightweight sail made of special materials that has electronics attached to it. And the guts of a cell phone nowadays can carry a navigation device, communication device, a camera, and in principle, you can launch all of these to a very high speed using this technology. And the idea is very similar to a sailboat. Instead of a wind reflecting off the sails of a sailboat and giving it a push, here light bounces off the sail and gives it a push. And potentially, you can accelerate a lightweight payload close to the speed of light this way. And perhaps other civilizations have developed that. So here is a brief history of my life. I was born in a small village on a farm in Israel, and I used to collect eggs every afternoon. So I'm a farm boy. Haven't changed much since then. You can see a picture of me driving a tractor, and I used to go to the hills reading philosophy books as a young kid. And then one day, an entrepreneur from Silicon Valley, Yuri Milner, showed up in my office and said, would you be interested in leading a project to reach the nearest star within our lifetime? Breakthrough Starshot. Didn't take me very long to say yes. And we've been working on the technology since then, a few years ago. This is called Starshot. The idea is to imagine an array of laser beams that combine to make a very powerful beam, and then releasing a sail above the atmosphere of the Earth such that this combined beam gives it enough push to bring it to a fifth of the speed of light within a few minutes. And across that time, it will move a distance that is about 5 times the distance to the moon. At that point, you stop the acceleration, and then it moves on a ballistic trajectory towards the target. And one can imagine launching such a sail once every day, because they're not very expensive. Most of the expense is the infrastructure of the laser. Then it takes, after those few minutes at the beginning, bringing it to a fraction of the speed of light, it would take about 20 years for the journey. And eventually, it will come close to Proxima B and take photographs of this planet and send them back to us. Now, that's not the end of the story, because it will take another 4 years for the signal to reach us. And then, eventually, we might be able to see what's happening on this planet. Is it green? Does it have vegetation? Is it blue? Does it have oceans? Or maybe it's desert-like. And that is the concept that we came up with for going outside the solar system in a relatively short time. And of course, there are many challenges You may worry about dust particles impinging on the spacecraft. And of course, if it moves at a fraction of the speed of light, each collision is just like a tiny atomic explosion on the surface. It releases a lot of energy. But we calculated that you don't need more than a coating of a few millimeters to protect the spacecraft against such particles. And there are many challenges involving the technologies that are needed to make this happen. We are only at the beginning of developing this technology, and it involves the photon engine, the sail, and other challenges like the communication between the spacecraft and Earth and so forth. And we are just at the beginning of the process. I'm being told that the policy issues will be even more challenging than the physics-related technology issues, because obviously one can use the same system for other purposes. And we are trying to make as much progress as possible scientifically on these challenges, such as the impact from dust or atoms in interstellar space at these very high speeds. The plan is that in the first decade to demonstrate that in principle these challenges can be met, and then dedicate the next decade to the construction of a prototype, and hopefully in our lifetime to have a system if we are able to do that. And one can imagine that there might be civilizations out there that had more time than we did, and so they managed to master this technology. So how can we find evidence for that? By searching for signals, leakage of radiation from those beams of light that are used to propel light sails. So one can search for that, especially for civilizations that try to transfer cargoes between one planet and another planet. When two planets line up along our line of sight, we might have a good chance of seeing that beam of light. So we can forecast when to look and search for it. And there are some flashes of light that are detected, for example, in the radio waves. These are called fast radio bursts that are still enigmatic. The popular view is that they originate from newly born neutron stars that are highly magnetized. So neutron stars are stars roughly the size of a city, about 10 kilometers in size, that have a mass of the sun. They have a density of nuclear matter, and they are formed when a massive star collapses. You can imagine, after they form, perhaps they possess very strong magnetic fields and can create these fast radio flashes. That's the most popular view, although we don't have evidence for that. And it may be a mixed bag. It may be that some fast radio bursts are natural in origin and others are artificial in origin. We have to find out. But what's clear is that we, as biological creatures, are not well suited to travel through space. In fact, if we spend more than a year in space, unprotected by the womb of the magnetic field of the Earth that protects us from cosmic rays, then a significant fraction of our brain cells will be damaged in that journey. That is not discussed in science fiction movies about going to Mars, establishing colonies, and so forth. There is a real health hazard. And you can imagine that sending out technologies into space would be much more optimal. You can imagine sending computers equipped with artificial intelligence and 3D printers such that they will produce whatever we want on the target planet out of the raw materials that exist out there. So we can send, especially if we are able to develop synthetic life in the laboratory ourselves, then we will know the recipe for making life, and we can design 3D printers that will make life wherever we want of the type that we want. There is no need to send life in harm's way if we can produce it there artificially. So it seems most natural for technological equipment to be sent out to space. And we have sent Voyager 1, Voyager 2, New Horizons is making its way out of the solar system. So you expect other civilizations to have done the same if they had long enough time. And there might be some traffic out there that we haven't noticed because it's difficult to see these small objects with existing telescopes outside the solar system, especially if they're very small, if they're Starshot-like objects. They might be passing by and we haven't noticed. And you can imagine even that civilizations travel on larger scales than galaxies, because one thing we know about the universe is that it's not only expanding, but the expansion of the universe is accelerating with time. And so that means that all the galaxies far away from us eventually will recede away from us at a speed greater than the speed of light. We won't be able to learn about their whereabouts. We won't be able to go and visit them beyond a certain time in the future, because space itself is expanding at an accelerated speed, and each and every one of those galaxies that are not bound to us will eventually reach the speed of light, and we won't be able to figure out what happens there and get any signal from that galaxy beyond that time. There is a horizon around us that we can observe, and the galaxies will all exit from that horizon if the accelerated expansion continues. So if you worry about the long-term future, you might want to go to the place where most of the resources exist. These are called clusters of galaxies. You might imagine civilizations migrating to where the party is, where most of them find most resources. That's on large cosmic scales. And the fundamental question is, why haven't we found evidence? This question was posed by Enrico Fermi about 70 years ago, after having lunch with his research group. He basically said, when they talked about extraterrestrial civilizations, he said, well, if they're out there, where is everybody? Why haven't we seen them? And the most natural answer to this question is that possibly most of them are dead by now. We know from our own experience that developing the advanced technologies we have brings in the risk of self-destruction. So you can imagine that they have a short lifetime. But that doesn't mean that you cannot find evidence for them, because they left scars on their home planets in the form of burnt-up surfaces or polluted atmospheres, or photovoltaic cells that transfer light from the permanent day side to the permanent night side. So one can do space archaeology and search for technological signatures of dead civilizations. That's something we can do with existing telescopes. That would be one way to figure out if there was somebody out there that is not around anymore. And look for megastructures around other stars, for example. And my hope is that this will be an important history lesson for us. By finding dead civilizations that didn't behave properly, they were not kind to each other or to their planet, we will learn an important lesson to do better and avoid a similar fate. So potentially, we can find evidence for life by looking at fingerprints in the atmospheres of planets as they transit their host star. One can search for oxygen, but one can search also for industrial pollution this way. And by the way, if the planet was outside the habitable zone, if it was too cold to start with, this might be a way of terraforming a planet, making it habitable. So it may not always be unintentional or unintelligent to do. Sometimes you might want to warm up a planet by putting a blanket over it, keeping it warmer. can imagine looking for solar cells on Proxima B. The permanent day side is constantly illuminated, and in principle, you can create electricity that would light up the permanent night side, or transfer heat. And it's possible to tell that without too much effort, because if you watch the light curve of the planet, once again, you can tell the temperature difference between the day and night side without resolving the planet. And you can tell whether there is artificial light on the night side, just from the light curve, without resolving the planet, just from the amount of light that you see at different phases in the orbit of the planet around the host star. You can also look for the reflectivity of the surface. If there are photovoltaic cells that are using the light from the star to produce electricity or heat, then they have a different reflectivity. So for example, vegetation has the so-called red edge. Vegetation, like trees or plants, they don't need infrared light because it can be used for photosynthesis. They only use up ultraviolet light. And so what you see is that our planet that has a lot of vegetation on the surface shows a red edge, a very significant increase of reflectivity at wavelengths that are longer than red light. And the same may happen for photovoltaic cells that use only energetic photons, and you will see an edge which is not the same as for vegetation, but you can associate with electronics. Finally, I wanted to mention that the things that we in particular care about, such as precious metals, like the gold in my wedding band. This gold, you might ask, where did it come from? And thanks to the LIGO observatory that detected gravitational waves from collisions of black holes and neutron stars, a couple of years ago, it detected gravitational waves, ripples in space-time from the merger of two neutron stars, and that was followed by light that was emitted from the same process, which astronomers can interpret and analyze and infer that elements like gold were produced in that process, where neutron material from the neutron stars was ejected into space, and it's unstable, and then it decays radioactively into elements like gold. This is called our process material. And so we believe, astronomers now think, that elements like gold and uranium, very heavy elements, were produced in neutron star collisions. Next time you look at your wedding ring, if it's made of gold, think about the fact that this material was inside a neutron star before it got on your finger. But obviously, we live in a typical spot in the Milky Way galaxy, and there are other places closer to the sites of neutron star mergers where you would find much more gold and much more uranium. So if there is a civilization out there, you might be wary about contacting it. Because it might have developed nuclear weapons much more effectively than we do, and on the other hand, it might have much more gold than we have. Molybdenum is another element that is produced in these collisions, and it is extremely important for life as we know it. So elements that we find to be rare here on Earth might not be rare in other places. To the economists in the audience, this offers a great prospect for enriching your bank account, except that when you have a lot of a rare material, then it's not rare anymore and the value goes down. So you have to take that into account. And my hope is that once we leave the solar system and venture into interstellar space, we will get a message back saying, welcome to the Interstellar Club. Thank you.